Hello, my name is Chayut Kovitchindachai, and I am here to present my Polygence project, Negative Emissions Technologies, an overview of direct air capture. Here are some keywords that you will need to know throughout this presentation. And as this is an asynchronous presentation, please feel free to stop the video now to take a look at these different keywords that will be good to know throughout the slide as it will help with understanding or comprehension. So let's start. What are negative emissions technologies? Negative emissions technologies, or NETs, are technologies with the main goal of reducing overall carbon emissions and strive for the net zero emissions, or NZE, by 2050. Some of these NETs include direct air capture, DAC, bioenergy with carbon capture and sequestration, BECCS, coastal blue carbon, CBC, and carbon mineralization. So, what is direct air capture? Well, direct air capture is a relatively new NET, and the concept of it was only emerged in 1999, and the first operational plant was only implemented in 2021 in Iceland. So, what is the big deal? DAC, unlike other NETs, is a more space efficient and can operate in a variety of climates and environments, which minimizes its impact on agriculture and other land uses, as well as the carbon dioxide captured by DAC can also be used in products like food and beverage, metal fabrication, cooling for refrigerators, fire suppression, and stimulating plant growth. So how does DAC work? Well, DAC works by, well, first of all, DAC is split up into two different categories. The first one being solid direct air capture, SDACs, and liquid direct air capture, LDACs. The main difference between these two is that one uses a solid sorbent while the other one uses a liquid sorbent. To start off, let's explain how the SDACs work. SDAC uses a unit with fans, a modular unit with fans to draw in air, which they would then go through sorbent filters, which would only absorb CO2 while allowing clean air to pass. This process would keep going on until the filters are full, and then the modular unit would close and heat up in order to make concentrated CO2, which is then released for storage or sequestered underground. LDACs, on the other hand, is a bit more complicated as it works on two different loops. The first loop uses an air contractor, which uses chemical solutions to draw in CO2, which would then turn it into carbonate salt and be moved to a pellet reactor to remove the carbonate from the solution, which would then be reused into the air contractor, and the carbonate, which is now in the pellets, would go to the calcinator, which is now the second loop. The pellets would be heated in order to release the CO2 gas, which is then captured for storage and sequestration, stored or sequestered. This pellet would then be reused using a slaker, and it will be recycled and then put back into the pellet reactor. Well, so that was quite a lot of information. So what are the benefits? So let's first compare the energy usage, water usage, and possible sorbents of SDACs and LDACs. So comparing the energy usage of both, we can see that SDACs use a considerable amount more of energy. And for comparison, a gigajoule is enough to power an average American home for a week. And comparing both of their water usages, we can see that SDACs actually produce water or has the potential to produce water, while LDAC uses 50 tons of water per ton of CO2. And For comparison, 50 tons of water takes up 50 cubic meters of space. That's quite a lot. And what and when we compare the two possible sorbents of SDACs and LDACs, we can see that the possible sorbents of SDACs are solid, and the possible solid sorbents of LDACs are liquids. So, what are the benefits and challenges of SDACs? Well, the benefits of SDAC is that there is possible water production, it's less capital intensive, it's modular, as well as it is likely to see a cost reduction, as the challenges are more energy intensive and requires manual maintenance for sorbent replacement. LDAC, the benefits of LDACs lies in its less energy intensive, as well as it's using commercial surf solvent, and as well as it is for large scale carbon captures. While its challenges is that it is more capital intensive, it relies on natural gas combustion for solvent regeneration. So how does it compare to other NETs? Well, first of all, let's have a small overview of the three NETs that we are going to be looking at. First one being bioenergy with carbon capture and sequestration. Well, BECCS for short. BECCS uses biomass like wood, crops, and manure to create heat, power, or hydrogen, and it's during this process, it also produces carbon, which would then be captured and transported to be sequestered. The benefits of this is that it provides stable and renewable electricity, while the challenges is that it takes up large amounts of arable and fertile land, as well as it not being as efficient as other NETs. Second up on the list is coastal blue carbon, or CBC. CBC relies on plant life in coastal and wetland ecosystems like microplankton, algae, seagrass, kelp, and mangroves to act as carbon sinks. CBC preserves, protects, and restores these marine ecosystems in order to create a carbon sink that can absorb and sequester large amounts of carbon for an indefinite amount of time. The benefits of CBC is that there are positive effects and benefits for both the local wildlife and local communities. It is also much faster at absorbing and sequestering carbon dioxide, around 2 to 10 times faster than tropical forests, as well as having a large global warming reduction potential. Challenges of CBC, however, is that it is very capital intensive and also has a lack of permeance, which means that the restored ecosystems will eventually degrade and release carbon captured if not constantly maintained. The third on the chopping block is carbon mineralization. Carbon mineralization is a process when CO2 becomes a solid through chemical reactions as it is exposed to certain rocks. How we use carbon mineralization is by injecting CO2 into certain deposits of these rocks using heavy machinery. The benefits of mineralization is that, unlike sequestration, mineralized carbon cannot escape into the atmosphere, as well as there being an abundance of reserves, specifically around 3,000 gigatons of storage potential in just America alone. And for comparison, the world produced around 36.3 gigatons of carbon dioxide in 2021, which means that just this deposit or storage potential can last us many decades, many decades. And the challenges of mineralization, however, is that there is a potential to trigger earthquakes with the injection of CO2 into geological formations, as well as it having the chance to negatively impact underground and surface ecosystems, as well as its large water usage. So that was probably a lot of information all at once. So here is there. This is a table that compares these four NETs together, having comparing their main principles, advantages, challenges, uh, costs, current storage, as well as the materials that they rely on. And as I do not want to bore you with a 20-minute talk over a table that can be easily read in 5 minutes, please feel free to pause the video here and also on the next slide and on read and compare these different statistics yourself. All right. Well, so which NET is the best of the four? Well, although each method has its benefits and constraints. For example, DAC is efficient and takes up less space, but at the high cost of higher energy usage and thus higher operating costs. BECCS tends to be cheaper, however, it requires a lot of space, which space and arable land, which means that it negatively impacts agriculture. CBC has one of the most potential to absorb and sequester huge amounts of carbon dioxide, but because of the steep cost to restore and maintain marine ecosystems, it is bottlenecked. And carbon realization has large amounts of reserves available for use. However, there are risks of possible earthquakes and negative impacts on the environment. Well, so Well, although no method completely triumphs over the others, DAC has the largest room and potential to grow because it is still relatively new. It is constantly undergoing development as well as developing new innovative methods. One of these methods being the electrosound adsorption, which is estimated to bring costs down to $50 to $150 per ton of CO2. This decrease from $50 to $600 per ton of CO2 would greatly impact DAC and allow it to expand its operations further. However, funding and resources should not be dedicated to just one NET, as funding and resources should also be provided to NETs that helps to protect and preserve biodiversity like CBC, as since although DAC shows promise, we can't ignore the potential that other NETs show either. So, as such, when we strive towards a better future, I believe that it is important to continue innovating and developing these NETs, as doing so would protect and preserve biodiversity, as well as the livelihood of all the organisms living on this floating rock. Thank you.